Hi, my name is Nilima Prasad. So today we are going to explore the computer vision task of multi-object tracking. So what is multi-object tracking? The goal of it is to simultaneously track multiple objects in a dynamic scene. So applications of this could include surveillance and autonomous driving. But how do we go about doing this? So the most common approach is called tracking by detection. So this approach is divided usually into two parts. One is to identify and locate the object, and the second task is to associate them across multiple frames. So, although this is the most common approach, it has its limitations. One of which is that it's computationally expensive and it relies on prior knowledge, and the tracking quality degrades as the number of objects that you need to track increases. Moreover, there's many challenges in maintaining consistent object identities over time, especially if there's occlusions. That means if one object is hidden behind another one, and it makes it much harder in a complicated scene like that for tracking by detection methods to work. So is there an alternative? Well, a less common approach is end-to-end tracking. And the goal of this is to streamline the tracking process by combining it within a single integrated framework, thus removing the distinct models for tracking. So possible benefits of this can include robustness and accuracy improvements, tracking without relying on separate stages like the detection and then the association, but rather having it streamlined. And the third would be that it would be able to handle complex scenes with occlusions much better. So my research question would then be, what are the differences between existing end-to-end tracking methods? Because although we're combining it within a single integrated framework, this of course can have many different ways to go about doing this. And are they superior to tracking by detection methods overall? So my experiment outline was to choose three models that provided end-to-end tracking algorithms for multi-object tracking. I then implemented and evaluated these papers based on a data set and certain evaluation metrics. Finally, I compared the results. After I found the best model that provided the end-to-end tracking, I compared that with the state-of-the-art tracking by detection model in order to determine which approach is indeed better for multi-object tracking. So the first paper that I chose was a Siamese multi-object tracking called SIAM mode. And it is a region-based network that detects and associates object instances simultaneously. So it includes a motion model that estimates the instance's movement between two frames and associates the detections, as you can see in the diagram below. The second algorithm I chose was TrackFormer, and this is a model that jointly performs object detection and tracking by attention with an encoder-decoder transformer architecture. So it uses transformers, and it is able to compute the attention between the input image features and the track object queries, and it outputs the bounding boxes that you see below with the assigned identities. So it takes both tasks and combines them into one using transformers. The third approach actually stems from this algorithm called Motor. And Motor is an end-to-end transformer-based framework. However, it had extremely poor detection performance when it was first implemented. So the authors actually bootstrapped it with a additional pre-trained object detector called YOLUX, and for better detection results. So comparing these three papers gave us these results. So I was able to test and implement each of these algorithms on the MOT17 dataset, and that is a benchmark multi-object tracking dataset that contains 7 different indoor and outdoor scenes. Now, the evaluation metrics I used was MOTA, which is multiple object tracking accuracy. So the higher the score, the better. And IDF1, which is the ratio of correctly identified detections over the average number of ground truth detections. And finally, frames per second. So with both of those scores, the higher the score, the better. So as you can see, the Motor V2 won in the sense that it had much higher MOTA scores and it had a higher IDF1 score. However, it was the slowest algorithm out of the three. Nevertheless, I chose this as the best method thus far for end-to-end tracking. Now I compared it to SmileTrack. So SmileTrack has state-of-the-art performance as a tracking by detection method. So testing this against my end-to-end algorithm showed that SmileTrack actually had higher scores of 81.1 for MOTA and 80.5 for IDF1. It was also more efficient. And I think this had to do with a superior object detector algorithm that they use, as well as the re-identification model. So they use this model, and with that model, the scores are actually lower than what's presented. However, it's much faster. But without it, it only has 5.9 frames per second, which means that it's much slower than both SciAm-Mote and TrackFormer. So it has its positives and its negatives, but overall, I would say that it has superior performance. So what is the conclusion? Each method has its advantages and disadvantages, but what did we learn from this project? So learning more about the various multi-tracking approaches will grant us deeper understanding about the best methods for multi-object tracking, as well as how to combine approaches for even better results in the future. So this study was integral in that it showed the variations in end-to-end tracking models and how by combining both approaches, such as bootstrapping a detector, can lead to even better results. So now that we have more of an understanding, we can think of future work, such as maybe bootstrapping an even better detector to Motor V2, or combining both methods to create something even better now that we have this understanding. Thank you so much.